Okay, so in this example, this is what it's. So we want to know what the iodate concentration is going to be when we have a saturated solution. So that means that the maximum number of ions that can be dissolved are dissolved in this solution of copper iodate. And there's the formula for copper iodate, which is going to be very important in writing that that dissociation equation. The KSP is given as this number right here. Okay, so if we go back to our notes and we take a look at those steps. Where were those? Right here. Okay, so the first thing we got to do is write the equilibrium equation. Write the equilibrium equation. Let's do that. So Cu iO3 2 is going to dissolve and come to equilibrium, and it's going to make what? How are those ions going to break apart? What's the ratio of the sort of creation of those ions? We're going to have Cu, and it was a Cu2, so that's Cu2 plus, and we're going to have the iodate ion, right? Is that the way it's going to be? It's going to be 1-to-1? Right, because look at this. We've got 1 mole, really, or 1 part in this compound, and then we've got 2 parts of the iodate. So this is going to be a 2. Everyone see that? So basically we need to balance the equation. Okay? Make sure it's balanced. That's really what you're trying to do. So we've got a 1 here and a 1 here. And remember, I like you to write the coefficients of the molar ratios for chemical equations as 1s. Write those down, please. So make sure you label that. Okay, so that's step number 1. Good with that? Step number 2, let's use a variable to represent expressions for each ion. Okay? Oops. So, this is the kind of tricky part for this type of question. All right? For every 1 mole of CuIO32, we get 1 part, or 1 mole, of Cu2 plus, right? But we get double the amount, or 2 times the amount, of iodate ion. You see that? So the expression for Cu is at 1x, and for iodate is 2x because of this 2 here. You good with that? Okay. Step 3. Oh, we have step 3? Step 3. Write the KSP expression including values and the variables. So the KSP, let's just do the initial. KSP has got to equal the concentration of Cu2 plus to the power of 1 times the concentration of iO3 minus to the power of 2, right? Because it's the same idea as the KEQ expression. So now if I filled in the numbers and the variables, I have 7.41 times 10 to the negative 8 equals, and this is where it gets a little bit trippy, and usually students are like, wait. What goes in here? Cu2 plus is x. iO3 minus is 2x. The KSP expression says I have to square it. So yes, 2x and square it. Double the x and square it. Trust me, that's how it goes. Okay? So yes, it's like, no, don't do that. Aren't you doing the same thing twice? No, you're not doing the same thing twice. Okay? It's 2x and it's squared. All right, so that's what you really want now. Now you want to solve for x. Okay? So on this side we have, this is going to be 4x squared times x. That's going to be 4x cubed. So 7.41 times 10 to the negative 8, we divide that by 4, okay, because we want to get x by itself, so let's divide by 4 first. 7.41, and scientific notation, times 10 to the negative 8, okay, and we're going to divide that by 4. 1.85 times 10 to the negative 8 equals x cubed. To get x by itself now, I take the cube root. So we'll do that. Where's my cube root button on this calculator? There we go. Cube root of, and we'll just stick that whole answer in there. We get 0.0026. So x equals 0.0026. Okay. All right. I think that looks okay. You guys okay with that? So what does that mean, though? What does it actually mean? Well, here we go. I guess this number means that the concentration of Cu2 plus is that value of x, right? 0.0026. What is the question actually asking for? The concentration of iodates. So guess what? IO3 minus, we have to go 2 times that number. Everyone see that? Times 2.00529. And of course that would be molar for both. Significant figures, if you're wondering how many decimal places you want to go to, I won't be a big stickler on that. I mean, I'm not going to hammer you too hard for sig figs. I'm mostly concerned about the rest of it. But if you're in an analytical situation, this is 3 sig figs right here. Did we use any other value that was less? Can't count the 1 and the 2 in the equation. So 3, you'd go to 3, which we actually have here already done. Okay? Yes?
Why are we not plugging in x value in KSP equation?
We are plugging the x value in the KSP equation.
So are we squaring it or multiplying?
See, this is the x, and this is the 2x. And here, x, 2x. KSP, right here, goes right there.
So are we not squaring it?
Yeah. No, I squared it. Okay, so there's a step in here that I missed, that I didn't write down, right? So 2x squared is what? That's 4x squared. Times x is 4x cubed.
And when you got the x value?
So when I got the x value, yes, right here.
Do you want
You're wondering why I don't put the x value in here.
Yeah.
You don't do that.
Yeah.
If you wanted to check to see if you got the right x value, I suppose you could plug this value in and double it and put that there and square it and then times the x value again to see if you got the KSP. But you see, what we're looking for here is just this part, the concentration part, just that. And that is actually just 2x. So no, you don't put this back into KSP because that's where you got it from, right?
Right.
That's where you got it from. So if you put it back in there, what are you doing? You're just checking your math? That's good. But you don't need to put it in there. Instead, you need to go to, hey, right here, 2x. And there's your answer. Okay? Good question. If you want to check your work, you could do that, but that doesn't give you the answer, no. What that'll do is if you plug this back in here, it'll just confirm the KSP. Good. Any other questions? Yes. We'll go back to those steps. So here are the steps again. If you want to finish copying those down, that's how you solve these questions.